are delighted to welcome our viewers back to the crystal clear electronics videos. For today's video, I've brought you a working model of a motor I built when I was in 7th grade, when I first started learning about physics and was immediately fascinated by its diversity and complexity. Several physical phenomena can be observed during its operation. There are two permanent magnets on the side of the motor. These simultaneously exert both a pull and a push force on the coils of the rotating part, where electricity flows through, creating a magnetic field around them, and interact with the magnetic field on the permanent magnets. In addition, the law of conservation of energy mentioned in the previous section can be observed, since the energy supplied by the power supply is converted partly into kinetic energy and partly into thermal energy at the connection points due to friction. That's all I wanted to say in this section about how this model works. If you are interested in more about the world of DC motors, check out the 13th video. Ambrus Zelei has already borrowed this model from me and will talk more about how it works. Let's go with the revision of basic physics with Mr. Danyi Béla. What are we going to talk about in this part?
In this section, we review some of the basic concepts and context in electrostatics. Several definitions, relationships, and derivations are given, but don't worry, we'll take you step by step. Starting with the concept of the electric charge, we'll cover the characterization of electric fields, electric potential, and even charge storage. I'm sure that by the end, everyone will have the whole picture. The electric charge is a basic quality of certain particles that determines the extent how they participate in electrical interactions. Charge as a physical quantity is usually denoted by the letter capital Q. Its unit of measurement is coulomb, which is represented by capital C. Atoms, molecules, and extensive bodies can be charged as well. The charge of extensive objects is caused by the excess or lack of an elementary particle called the electron. The electron has a low negative charge.
If the charge of matter is determined by the amount of electrons in it, which have a negative charge, then we cannot find extended bodies in nature with a positive charge, right?
Of course we can find them. In materials, normally each electron has a single positive charged particle pair, called the proton. So when looking from the outside, the material appears neutral and its total charge is zero. Occasionally, there can be cases when there are excess electrons or lack of electrons, for example, when two bodies are rubbed together. The positive protons cannot move, but some of the negative electrons can. So by rubbing, the electrons can move from one body to another, disrupting the balance of charges. When this happens, we say that the body is in an electrically charged state. The interaction between such bodies is called an electrical interaction, which can be detected as repulsion or attraction. Experience has shown that bodies with the same sign of charge are repelled, but those with the opposite sign of charge attract each other, thereby, in both cases, they act on each other by force. The electrostatic force is one of the fundamental interactions in physics. Its size is described by the formula F equals K times Q1.Q2 over R squared, as shown on the screen, called Coulomb's law in case of point charges. The number K is a constant. Its value is approximately 9 times 10 to the power of 9. Q1 and Q2 are the signed charges of the two bodies, negative for negative charge and positive for positive charge. And R is the distance between the two charges. It's obvious that the higher the charging of the two bodies, the greater the attracting or repulsive force is between them. Increasing the distance reduces the effect squarely, that is, at twice the distance, only a quarter of the force between the two bodies exists. The law also states that if the Coulomb force is positive, then it is a repulsive force, since the sign of the two charges must be the same. If this force is negative, then we speak of an attractive effect, since the two charges must be opposite.
Does this also mean that if you deposit a charge somewhere in space, it will exert a force on another charge deposited at an optional distance without contact? You are yet to mention what mediates this force.
This question logically arises. It leads to another concept, that is the electric field. This field mediates the forces between electric charges. Each charge has its own electric field, of which it is the source. At this point, another question may arise. How can we define the electric field associated with a given charge? This brings us to the next concept, the electric field strength.
Kérdéshez is, hogy miként tudnánk jellemezni egy konkrét töltéshez tartozó elektromos mezőt. Ehhez kapcsolódóan pedig akkor beszélhetünk egy kicsit az elektromos térerősség fogalmáról is. Vegyünk egy töltéssel
Take a charged point-like body
testet, és
and place it somewhere in space, far away from other bodies,
helyezzünk el a közelében,
and place a positive charge near to it, called test charge,
nevezzünk próbatöltésnek, és
and measure how much force it exerts.
hat erre a próbatöltésre.
If the resulting force is divided by the charge of the test charge, then a physical quantity is obtained, which is characteristic of this point of the space. This quantity is called electrical field strength, it is denoted by capital E, and its unit of measurement is volts per meters. E equals F over Q written down.
Matematikailag megfogalmazva, akkor ezt úgy is felírhatjuk, hogy az
If the Coulomb force formula is substituted for F, then we get that the electric field strength is independent of the charge of the test charge, it is dependent only of the charge of the charged body and the distance of the measurement. A field strength value can be assigned to all points of the space with this thought.
és a mérés távolságától függ. Ennek alapján a tér minden pontjához
The electric charges create an electric field around them, whose magnitude is indicated by the value of electric field strength.
amelynek nagyságát az elektromos térerősségért.
Where the value of electric field strength is higher, there is a greater force on a charge placed there.
Nagyobb erő. Az előző videóban már beszéltünk
In the previous video, we talked about the fact that when force causes displacement, we're talking about work. This is, of course, also the case with electrical forces. Let's also try to define the electric field in terms of its ability to work. This brings us to the concept of electrical voltage. Let's explore this too.
vezet minket a következő fogalmunkhoz, az elektromos feszültséghez. Az egyszerűség kedvéért vegyünk egy olyan esetet,
To understand this better, take a case when the electric field strength at all points of the space is the same in size and direction, but not zero. These fields are called homogeneous. Put a positive test charge in this space. Because the Coulomb force affects it, it'll move. The starting point of the displacement is marked with A, and the end point is marked with B.
az elektromos tér munkát végez rajta.
The electric field exerts work on it during its movement, which we can describe with the previously mentioned formula F times S. If we substitute the force for the electric field strength, defined by F equals E times Q, we obtain the following formula. WAB equals F times S equals E times Q times S AB. It can be seen that the work, which has been done, is directly proportional to the size of the test charge Q, electric field strength E, and the capital displacement SAB. This is also true if the electrical field isn't constant in space. If you want to get a quantity that gives you the ability to produce work at a particular point in the space, then it should be independent of the test charge. Dividing the work by the charge of the test charge, we get this amount. Its name is electrical voltage, it is denoted by the letter capital U, and its unit of measurement is volt. In mathematical terms, the voltage measured between points A and B can be given by the work done by the electric field divided by the test charge. Substituting the previous formula and performing the simplification, we obtain that the value of the voltage will be proportional to the magnitude of the field strength and the amount of displacement. Based on the above, the voltage can only be interpreted between 2 points. If we agree on a 0 point, then all the other voltages are understood to that point, and in electrical circuits, the 0 point is the ground, often just GND for short.
Elektromos áramkörökben a nulla pont szerepét a földelés tölti be.
Ha jól gondolom.
If I'm not mistaken, the following part will be about the capacitors. As a demonstration, I have brought you some capacitors of different capacitances and designed for different voltages. They are also different in sizes, from the size of my finger down to 1 × 0.5 mm, which are hard to see with the naked eye. Before the video, I dismantled the casing of one of these electrolytic capacitors so that the viewers can see that we are talking about a parallel plate capacitor which is wound up in the cylinder. I thought these would be interesting to show in the video. Can you tell us a little about them?
Ez esetben is síkkondenzátorról beszélünk, amely egy ilyen hengerszerűen van föltekerve. Gondoltam, ez látványos lesz
Igen, szuper.
a videóban. Beszélnél ezekről néhány szót nekünk?
Hát kezdjük akkor először azzal, hogy...
Let's start with explaining what capacitors are, although you already mentioned some details. The capacitor is a device for accumulating electrical charge. Many types are made. The difference can be in voltage, capacity, and also in sizes as shown.
Van többféle, amit már mondtál, a feszültség és a kapacitás értékek is mások lehetnek, de látjuk, hogy a méretekben is alapvető különbségek lehetnek. Ennek az egyik legegyszerűbb példája...
The simplest is the so-called plate capacitor, which has a double-sided metal plate and insulating material, for example air, between them.
Tulajdonképpen két egymással párhuzamosan elhelyezett fém lemezből, ezeket hívjuk fegyverzeteknek áll, illetőleg a közöttük lévő
The quality of the insulating material, the distance and the size of the metal plates are affecting the capacity of the capacitors, which is one of the most important quality because it shows us how much voltage can we store in the capacitor.
távolsága és mérete mind együtt befolyásolja a kapacitás értékét a kondenzátoroknak, ami az egyik legfőbb tulajdonsága, hiszen ez mondja meg, hogy mennyi töltést tudunk rajta tárolni.
If a positive terminal of a galvanic cell is connected to one of the plates, the negative is connected to the other by a wire, then the plates will have an equal but opposite sign charge, i.e., an electron excess on the negatively charged plate and a lack of electrons on the positive plate.
Elektronhiány lesz.
If we were able to measure the charge level of the capacitor's plates while charging, then we would experience that the measured charge is directly proportional to the voltage between the plates.
Arányos a fegyverzetek közé kapcsolt feszültséggel.
In other words, if you connect twice as high voltage to the capacitor, then it will double the charge on the plates.
Két mennyiség közötti arányossági tény
The proportionality between the two amounts is the capacity, its symbol is capital C, and its units of measurement are farads with capital F. Mathematically written, Q equals C times U, where the amount of charge is represented by Q. Capacity shows the capacitor's charge storage capacity. The higher the capacitor's capacity, the more charge can be stored at the same voltage.
tudunk tárolni ugyanakkor a feszültség mellett.
I'll borrow a capacitor.
Legyen ez. A kondenzátor
When the capacitor is charged, it stores energy.
energiát tárol. Ha egy kondenzátor
When a capacitor is charging and its plates are suddenly short-circuited with a wire, we experience that the conductor gets warm.
hogy a vezető felmelegszik.
This means that the energy of the wire has increased, which can only come from the capacitor.
A kondenzátorból származhat.
Köszönjük.
Thank you, Béla, for the repetition. Now we must say goodbye for a short time.
Tartsatok velünk.
Stay tuned for the next episode, where we are going to talk about the electric current and some interesting effects of it. Bye!
Sziasztok!